This flick will continue discussing the previous chapter on mass and energy analysis of control volumes, but focusing on flow work and energy analysis of steady flow systems. First, we will learn about flow work and the energy of a flowing fluid. Some work is required to push the mass into or out of the control volume. This work is known as the flow work or flow energy, and it is necessary for maintaining a continuous flow through a control volume. To obtain a relation for flow work, consider a fluid element of volume V as illustrated here. Pretend the fluid immediately upstream as an imaginary piston that forces this fluid element to enter the control volume. The fluid element can be chosen to be sufficiently small so that it has uniform properties throughout. If the fluid pressure is P and the cross-sectional area of the fluid element is A, the force applied to the fluid element by the imaginary piston becomes P times A. This force must act through a distance L to push the entire fluid element into the control volume. Thus, the work done in pushing the fluid element across the boundary is equal to P times V. The flow work relation is the same whether the fluid is pushed into or out of the control volume. Now let us learn how to estimate the total energy of a flowing fluid. The flowing fluid's total energy consists of flow energy, kinetic energy, internal energy, and potential energy. On a unit mass basis, denoted by theta, it is presented as in the given form. As we already know, the combination of PV plus U equals the enthalpy H, so the relation reduces to the following manner. Many engineering devices such as turbines, compressors, and nozzles operate for long periods under the same conditions once the short startup period is completed. Steady operation is established and they are classified as steady flow devices. Processes involving such devices can be represented as an idealized process called the steady flow process. During a steady flow process, no intensive or extensive properties within the control volume change with time. Thus, the volume V, the mass M, and the total energy content E of the control volume remain constant. As a result, the total mass or energy entering the control volume must be equal to the total mass or energy leaving it. These observations greatly simplify the analysis. During a steady flow process, a control volume's total energy content remains constant. Thus, the change in the control volume's total energy is zero. Therefore, the amount of energy entering a control volume in all forms by heat, work, and mass must be equal to the amount of energy leaving it. Then, the rating form of the general energy balance reduces for a steady flow process to the following manner. The energy can be transferred by heat, work and mass only. The energy balance in the latest equation for a general steady flow system can also be written as follows. A more explicit and comprehensive expression is as in the given form. Consider, for example, a standard electric hot water heater under steady operation, as shown in a given illustration. A cold water stream with a mass flow rate m dot is continuously flowing into the water heater at state 1. A hot water stream of the same mass flow rate is continuously flowing out of it at state 2. The water heater is losing heat to the surrounding at a rate of Q dot out. The electric heating element supplies electrical work to the water at a rate of W dot in. During this process, no work is done by the control volume and heat is supplied into the control volume. Therefore, both terms can be cancelled out from the equation. When performing a general analytical study or solving a problem involving an unknown heat or work interaction, we need to assume a direction for the heat or work interactions. In such cases, it is common practice to assume heat to be transferred into the system as a heat input at a rate of Q dot. Work produced by the system as a work output at a rate of W dot. Obtaining a negative quantity for Q dot or W dot simply means that the assumed direction is wrong and should be reversed. For single stream devices, the steady flow energy balance equation becomes the following expression. Dividing the latest equation by m dot yields the energy balance on a unit mass basis. Suppose the changes in the fluid's kinetic and potential energies are negligible. In that case, the energy balance equation is reduced further in the following manner.